Hello, this is Dr. Nair and I am going to work on the worksheet number 2. This problem is regarding drawing resonance structures, and the first structure has a formal charge on nitrogen, positive charge, and on oxygen it has a negative charge. So maybe drawing the lone pair of electrons will make it more clear to show the movement of electrons, because when you show resonance structures you have to use the curved arrow formalism to show the movement of electrons either as lone pairs or from pi bonds. So in this case the resonance structure can be drawn by moving this pair of electrons over to this bond and simultaneously moving this pair of electrons onto the oxygen atom. Okay, we have to do this so as that the octet rule is not violated. Otherwise, nitrogen, if we do not do the second arrow, the nitrogen will end up having too many bonds. Correct? So the resultant structure, follow the arrow and draw it out. We have nitrogen now with a double bond to this oxygen atom. Again, keep the lone pairs. Now we have only two lone pairs because one of the pairs was used to form the bond. And then here we have a single bond to the oxygen because it pushed the pi electrons onto the oxygen atom. So this oxygen has three lone pairs, and then this bond remains intact. Now, if your original structure has a charge, then your resultant resonance structure should also have a charge. So this has a negative charge on this oxygen atom. Now the same oxygen atom is neutral, but the negative charge is on this one. So the formal charge on this oxygen is -1. Nitrogen again will have the positive charge, formal charge, because you can see that it has used its lone pair to form a bond. So whenever you see nitrogen with 4 bonds, give it a formal charge of +1. Okay, moving on to the next one. The negative charge is placed on this carbon atom here. Okay, so maybe if you draw this out with the hydrogens, or some of the hydrogens, not all of them, shown, might help you to understand it. Okay, so we have the double bonds here. Okay, and then this carbon atom actually has a hydrogen here and a hydrogen here, and then a lone pair of electrons too. That's how the structure is. So we are allowed to move pair of electrons from as lone pair or from pi bonds, but you are not allowed to move atoms in a resonance structure. Okay, so the way we would we can draw a second resonance structure. Actually, this molecule can have more than one resonance structure, but to draw one of them, you can move this pair of electrons here and take this pi electrons and place it over the carbon atom here. Okay, so the resultant structure would be the total number of atoms, carbon atoms, is 5. You did not touch this bond, so that remains intact. Use the lone pair of electrons to form a bond here, correct? So you have a bond here now, double bond. Sorry. And then we have a pair of electrons on this carbon atom, which now gets the negative charge. Okay. Ideally, you could have done a second resonance structure where you move this pair of electrons over to this carbon-carbon bond here, and then move this pair of electrons at the carbon at the end. Okay, so that could also result in a third resonance structure. The next one, again, if you look, it's good for us to draw the pair of electrons, lone pair of electrons on nitrogen atom, because that helps us to draw the resonance structures. So here you can see that the pair of electrons here can move to form a double bond with this double bond with the nitrogen, the carbon bond here, and Simultaneously, you have to break this pi bond and place the electrons onto this carbon atom. And this actually, again, this structure again can have more than one resonance structure, because you can move the pair of electrons on the entirety of this ring, or in other words, the pair of electrons can be delocalized over the entire ring. Okay? But since it is, we have only one box, you will draw one, but you should practice drawing all the resonance structures that are possible. Okay, so it's following the arrow. You can draw the resultant structure. So we have a benzene ring, but now it is one of the bonds is removed, and then we have a double bond with nitrogen with a lone pair of electrons was used to form the double bond, and now the pair of electrons is placed over here. Okay, so as I said, you can actually continue drawing this, where you can move these electrons to this carbon-carbon single bond. You make it into a pi bond now and break this one and move the pair of electrons here. Okay. So that's the question number 1. If you want, I can show you a couple more structures of this one on another page here. Okay, let's draw that structure one more time and see all the resonance structures that are possible for that molecule. So we'll start with that NH2, which we just drew in the box. Actually, we have to go back to that page because we forgot to put a charge on the nitrogen atom, because in the beginning we had a neutral structure, so our resultant structure should also be neutral, because the resonance rules say that you cannot have formal charges created in the resonance structure if the original structure doesn't have charge, right? So this is a neutral structure, so if you have a positive and a negative, it balances, and therefore this will also be a neutral structure. Okay, now as I was showing you, the other resonance structures that can be drawn for this molecule, so we still have the 2 pi bonds, and then we had a negative charge in this carbon atom. Correct? So the way you can do some more resonance structures is move this pair of electrons here, break this pi bond and put the electrons here. Resonance structures are separated by a double-headed arrow. So you can have this. NH2 still remains intact with a positive charge. We didn't change that. But now, see, this pair of electrons formed a bond here. Now we have a double bond here, and the pair of electrons decided to move to this carbon atom. One more can be drawn. Again, arrows help to direct the pair of electrons. This goes over to this carbon-carbon bond, and this resides onto this carbon atom. So the resultant structure would be, have a double bond here, and the pair of electrons on this carbon atom. And then finally, this goes over here, give the nitrogen the pair of electrons back, and you get the neutral structure. This is my final structure, and we give the nitrogen the pair of electrons. So these are the multiple structures that can be drawn for the molecule by moving the pair of electrons on the entirety of the ring. Okay, so now coming back to the next question on this worksheet. Identify the most acidic proton and explain your choice. So here there are many protons that are shown, right? And according to Lowry-Bronsted theory, protons can be donated by acids. So here we can see that there are several protons. The hydrogen atoms are can be given off in the form of a H plus ion, and that is what we refer to as a proton. So there are certain rules which help us to decide which one will be the most acidic. One is that if the hydrogen is connected to a more electronegative element, then that hydrogen is the more acidic hydrogen. So if you look at all these hydrogens, which I'm circling with a red color, these are all hydrogens which are attached to a carbon atom. Whereas the the hydrogen that is, which I have circled in green, is the one that's connected to a oxygen atom. So this phenomenon is called as elemental effect. That means to which element hydrogen is connected matters. If it is connected to a more electronegative element, that hydrogen or proton is more acidic than the proton that is connected to a less electronegative element. So by that reasoning, the hydrogen that is circled in green will be the most acidic proton. There is one more reason that if this proton is given off, then the conjugate base that results from the removal of this proton can be drawn like this. Okay, so if you recall, you have to maybe read a little bit about conjugate acids and bases. So when a proton is removed from an acid, the remaining part of the molecule is called as a conjugate base. So let's draw that out. The conjugate base of this molecule will look like this. Okay. Now I'm not going to draw this hydrogens, the red hydrogens, because well, I will have to draw this one, but not the one on the ring, because they are not the most acidic one, right? We decided that the one that is connected to the oxygen is the most acidic one. So we just need to draw the hydrogen, and again we'll go back and circle this. Okay. Oh, sorry, this we have drawn the conjugate base, right? So we don't need to draw the hydrogen anymore. So once the hydrogen is removed, the one that is circled in green, what is remaining is an oxygen atom with a negative charge, right? Because this hydrogen is leaving without taking any electrons with it. So the electrons here, which form the bond between oxygen and hydrogen, stay back on the oxygen. So oxygen gets a negative charge, and this is the conjugate base of the molecule that is given on your left side. So this conjugate base can actually be stabilized by resonance. How? See, this pair of electrons can move over here. Simultaneously, you can break this pair of electrons and leave it over here. So you can get multiple resonance structures. One of them I can draw, which is the one with a double bond to this oxygen atom, but then the pair of electrons are residing on this carbon atom. And so on. Just like we did in the previous example, this pair of electrons can be delocalized on the entirety of this ring, so we can do multiple resonance structures, which again is a reason why the hydrogen circled in green is the most acidic one, because the conjugate base is stabilized by resonance. And resonance is a phenomena of stability. So anytime a molecule or an ion can exhibit resonance, that gives it more stability. It's in a lower energy state. So when it was the parent molecule like this, it is slightly higher in energy than its conjugate base. So it has all the tendency to give off this proton circled in green, so that it can form a conjugate base, as shown on the right side here, which can further be stabilized by resonance. Okay, I hope you got that. So two effects are helping us to explain the most acidic proton in this molecule. One is the elemental effect, and the other is the resonance effect. Okay. The next question is asking us to consider this reaction below and identify the also showing using the curved arrow formalism, show the flow of electrons for this reaction. Okay. So here we have ammonia, and this is actually HNO3, an acid, nitric acid. And then a conjugate products are given. One is a base and one is an acid. So you have to use the curved arrow formalism. How to do that is we have to identify which one is the acid and which one is the base. And we can do that by looking at the product here. This is actually a positive charge, right? Okay. So if you look at this, nitrogen has, or the ammonia has gained a proton. So in other words, it has accepted a proton, right? So anything that accepts a proton is base. And anything that can donate a proton, it looks like the HNO3 was the one that donated the proton, is the acid. And the arrow formalism would be always from an electron rich to an electron poor. So the electron pair here is the nitrogen atom here with a pair of electrons is the one that's going to accept the proton, and simultaneously this pair of electrons are going to go on the oxygen atom, and that's what results in this conjugate acid and conjugate base. Okay. So these are the couple of questions on the worksheet number 2. Let's see if we can move on to the next one. Okay, here we go. So arrow formalism, drawing arrow formalism is very important because it tells you the direction of equilibrium also of the reaction, whether it is trying to move towards the forward direction or is more stable at the backward direction. Okay. The next question is asking about identifying the strongest acid, the base, and to predict the direction of equilibrium. So pKa is telling us which one would be a strong acid and which one would be a strong base. So the fact is, lower the pKa, stronger is the acid. So if pKa values are given, then you can easily identify which one is a strong acid and which one is a weak acid. So here see, pKa is 15.7, pKa is 18, so this one would be my stronger acid. So water is my stronger acid. So that's one fact. Second fact is that equilibrium always, or the reaction always proceeds from a stronger to a weaker acid. That is the fact. So that means it will help us to answer the part C, because if this is the stronger acid, then the equilibrium will predominantly lie towards the left side of the equation. Okay, so that means the water is going to act as the acid, this is going to act as my base, and the opposite reaction where potassium hydroxide KOH and this alcohol is being formed. So to answer the question, the strongest Lowry-Bronsted acid in this equation is D. The strongest Lowry-Bronsted base in this equation is base. Now it's asking the base, right? So that's C. And will this reaction take place in the as written? So you have to say no, because the reaction always proceeds from a stronger acid towards a weaker acid, and so it will go in the backward direction. So it has to be favored backwards, in the backwards direction. Next question. For the following compounds, arrange in the order of increasing acidity for the underlined hydrogen and explain your choices. So we are comparing an alcohol to a carboxylic acid. This is a proton that is acidic in nature. In this case also, this is the proton that is acidic in nature. Again, for the same reasoning, that the proton that is connected to the more electronegative element is the most acidic. So if you draw the skeletal structure of this CH3, CH2, OH, okay, this is what the alcohol looks like. And if you look at the skeletal structure of this compound, this is the Lewis structure, and maybe we should draw the lone pair of electrons too. Okay, so it's asking, why is this proton in the, or we have to tell which one is more acidic. So we can try to look at the 4 reasonings which helps us to figure out which one is more acidic. One is the elemental effect, where if the proton is connected to a more electronegative element, then it is more acidic. However, in this case, the proton is connected to oxygen, right? In both the examples, of a proton is connected to oxygen. So that doesn't help us to answer this question. So the second effect is resonance effect. And that is what will help us to answer which one would be more acidic. So what we need to do is, again, as in the previous question, we have to draw the conjugate base of these acids. So once the proton is removed, whatever is remaining is the conjugate base. So the conjugate base of this alcohol, of this molecule, is the one that's drawn here. And the conjugate base of this molecule is this one. In both cases, now oxygen has a negative charge. But in the molecule on the right side, which is your carboxylic acid, after the removal of the proton, the conjugate base can actually be stabilized by resonance, because this pair of electrons can go over here, and then this pair of electrons can go over here. So this conjugate base of the carboxylic acid can exist as a resonance structure, where the negative charge is now present on this oxygen. Now we have a double bond to the oxygen that's shown here. Okay? Whereas in this case, no resonance structure is possible for the conjugate base. Therefore, the proton connected to the oxygen in the carboxylic acid is more acidic. So you can say that the proton here is more acidic. So CH, the carboxylic acid, is more acidic than the alcohol. The next question, it's asking again with a few compounds that's given here. So you can draw this out. Now the first molecule has a few fluorine atoms. The second molecule has a few chlorine atoms. And the third one just has hydrogen atoms. Okay, and again, which is the acidic hydrogen? In all 3 cases, it's the one that is connected to the oxygen, the one that I've highlighted in red. So how to arrange them in the increasing order of acidity? Which one would be more acidic? So there is a third phenomena which helps us to identify the most acidic species other than resonance and elemental effect, and that's called as inductive effect. It's called as inductive effect. which means that if you have more electronegative elements present in the molecule, they tend to pull the electron density more towards itself, as a result of which the proton can be easily donated or given off. So that will make it more acidic. So the more electronegative elements that are present, more acidic will be the molecule. So in this case, since fluorine is the most electronegative element in the periodic table, and we have 3 of them here, they are going to act as an electron sink by pulling this electron density towards this side, as a result of which you can easily give off this proton, which again tells us that that molecule should be the most acidic. The next one would be the one which has chlorine, because chlorine is more electronegative than the hydrogen, right? So in this molecule, or in all the examples that are given, the one with the fluorine is the most acidic because of inductive effects. We can say this molecule is more acidic than the one that contains chlorine, which is more acidic than this one. So the trend of acidity is this way. Okay, finally there is a third group of molecules given, and here if you see, the protons are connected to nitrogen here, the protons are connected to carbon here, second one. Third is proton is connected to fluorine, and finally proton is connected to oxygen. So everywhere the acidic protons are the ones that are connected to these elements: nitrogen, is carbon, which here is fluorine, and then there is the oxygen atom. Here the elemental effect is going to help us answer the question. The proton that is connected to the most electronegative element is the most acidic. Which will be the most electronegative element? It's fluorine, correct? So HF is more acidic than NH3, which is more acidic than H2O, which is more acidic than CH4. Oh, sorry. Oxygen is more electronegative, right? My mistake. Okay. So it should be H2O more acidic than NH3, which is more acidic than CH4. So yeah, you can write it in this way, or you can write it in this way too, that CH4 is less acidic than NH3, which is less acidic than water, which is less acidic than HF. You can write it in any way, and that answers the question. Let's look at the next one, and this is based on intermolecular forces of attraction, IMFs. Intermolecular forces of attraction. So before I move into this, let's quickly summarize the 3 intermolecular forces of attraction you should know, which are prevalent in organic molecules. One is the London dispersion force. Second is dipole. And the third one, and the most strongest out of the 3, is hydrogen bonding. Again, you must have studied this in general chemistry. We abbreviate it as IMFs, and you should read this section in chapter 2, because a lot of organic molecule properties, physical properties especially, can be answered by understanding the type of intermolecular forces that are present in these molecules. So coming back to this question, we can list out the type of intermolecular forces that are present in this molecule. First one is an alcohol. Wherever you have a hydrogen connected to an electronegative element like oxygen, nitrogen, or fluorine, it indicates that the molecule will have hydrogen bonding. Okay, so if in this molecule, the alcohol molecule, this is an alcohol, OH is an alcohol group. We'll come to learn about that in chapter 3. But anyway, this molecule has an OH bond, which is a necessary condition for hydrogen bonding. So the type of intermolecular force that is present in this molecule is hydrogen bonding. So it is hydrogen bonding. In addition to London dispersion and dipole-dipole. Here this molecule will only have dipole-dipole and London dispersion, because London dispersion is an inherent intermolecular force present in all molecules. Okay, every organic molecule will have London dispersion force. So, and that is one of the weakest. This is the weakest and this is the strongest. So if a molecule exhibits hydrogen bonding, then definitely that's the one that will have a higher boiling point, because you need more energy to separate the molecules going from a liquid state to a gaseous state, which is what is meant by boiling. Alright, so we will circle our answer as this one to have the higher boiling point. Okay, higher boiling point. Alright, so that concludes our worksheet number 2, part 2, or chapter 2, part 2 worksheet. And I will follow this up with a third video of the worksheet which involves resonance structures.